Hi everyone, I'm Antonis. I'm a senior PhD student at Carnegie Mellon University, advised by the SIGCOMM, and today I'm very excited to talk to you about our work on SLOMO, a framework for contention-aware performance prediction NFV. Our protagonist for today's talk is Dwight, who now works as an NFV operator for his local ISP. Dwight was tasked with deploying a software firewall in the ISP's NFV cluster, such that its throughput SLA of 1 Gbps is met. In his small cluster, Dwight only has two deployment options, either co-located on server A with two already running NFs, or co-located on server B with three other NFs. The firewall throughput, if it runs solo on either server, would be 1.5 Gbps. Dwight tries both options before deciding where to spawn the firewall. He first tries server A, and he sees that the firewall can process 1.3 Gbps of traffic with no problem. He then moves to server B, and despite having followed standard deployment assumptions for NFV, he sees that his firewall can only process 0.7 Gbps of traffic, almost 50% lower than running it on server A. Dwight is extremely confused. What Dwight really needs is a tool to predict the expected throughput of his firewall for each co-location scenario, without actually having to deploy it beforehand. If anything, he knows that such a tool will be useful when he is in charge of bigger clusters with hundreds of servers and hundreds of combinations of co-running NFs. Now, let's formalize the prediction problem a bit more. Dwight is given a set of NFs. One of these NFs is the target, or the NF whose throughput he cares about. In a running example, that is the firewall. The remaining NFs the target will be co-located with are competitors. The question then is simple. What will the target's throughput be when it is co-located on the same server without competition? Our work, SLOMO, is a contention-aware performance prediction framework that perfectly meets Dwight's needs. SLOMO leverages a comprehensive, data-driven understanding of contention and builds efficient performance prediction models for any target NF. Indeed, SLOMO is accurate, with its average prediction error being less than 8%, which in comparison can be up to 60% better than the error of prior work. Let us now look at the agenda for this talk. First, we will look at how prior work has approached performance prediction in the past, and motivate through an analysis of contention mechanisms why the same insights of prior work no longer apply to today's NFV deployments. We will then revisit the prediction question through the lens of a blueprint for prediction that introduces contentiousness and sensitivity. Finally, we will address all the practical challenges that are associated with porting these concepts to the NFV realm. Let us begin with the first item in the agenda. Several prior works have demonstrated that performance degradation is the result of contention for hardware resources on the shared server. In the case of NFV, in particular, where competing applications are pinned to independent CPU cores and have isolated per NF NIC queues, these resources lie in the server's memory subsystem. Indeed, prior work showed that performance degradation in NFV stems from contention in the last level cache, and models the target throughput drop as a function of the aggregate cache access rate of its competitors. Specifically, performance is a function of the rate at which the competitors will be accessing the shared last level cache and evicting target data to DRAM. However, while the insights of prior work have been invaluable, when testing the cache access rate based model in our state-of-the-art NFV deployment that runs at line rates of up to 100 Gbps, we found that the error of its predictions was large, often up to 40%. While surprising at first, the inaccuracy of the predictions pointed in one clear direction, that our current understanding of contention mechanisms is insufficient, and until we improve on that, our prediction models cannot get any better. Therefore, to understand why cache access rate is an insufficient predictor, we look at other possible sources of contention through what we call the life of a packet. Specifically, we look at the set of hardware resources that are being used when the packet arrives at the NIC and until it's processed by the target NF. We find that contention in the memory subsystem is much more pervasive in a modern NFV deployment. As soon as a packet arrives at the NIC, DDIO, an optimization to traditional DMA, ensures that the packet is directly transferred to a slice of the last level cache dedicated to packet buffers of all co-running NFs. The NF will then read the packet over DPDK and will bring to the last level cache auxiliary data structures, such as rule tables, in order to process it. Therefore, we find that contention might happen both for available space in the DDIO slice of the cache and for space in the last level cache. In addition, competitors will also contend for available main memory bandwidth. In what follows, I will discuss the experiments that reveal these choke points. First, we'll look at contention during packet I/O, where slowdown is the result of packet buffer evictions from the DDIO subcache. In our experiment, we co-located a simple stateless firewall with competing L2 forwarding NFs, and across runs we increased the competitor's DDIO contention through packet size and traffic rate. The figure shows the firewall's normalized throughput as the competing DDIO occupancy increases for various packet rates. Our key observation regarding the source of contention is that as line rates go up and packet rates increase, DDIO becomes increasingly important. After DDIO space is depleted, which is indicated by the dashed red lines, target NF packets are evicted to DRAM and throughput drops by up to 10%. Let us now move on to the last level cache. The last level cache is a well-known source of contention, and a target NF experiences performance drop due to cache contention when its data structures are evicted to DRAM. To understand this more, we run an IP router that makes heavy LLC usage along with a synthetic competitor that applies various amount of incremental pressure to the cache. The graph shows the throughput drop of the target as a function of two variables of the competition. The red dashed line shows the cache occupancy of the target NF when it runs solo on the server. The takeaway from this figure is that competing cache occupancy and access rate are both responsible for shaping LLC contention. Indeed, when the target and competitor do not exhaust the available cache space, competing cache occupancy is key to quantifying contention. After that critical threshold, competing cache access rate starts gaining importance as a predictor. Finally, the last source of contention we identify in this work is main memory bandwidth. In this graph, we show the example of an IP router competing for main memory bandwidth with aggressive synthetic competitors. The competitors are configured to compete with each other in last level cache, but not with the target, and observe the target's performance drop as a function of the used main memory bandwidth. What is happening under the hood is that evictions in both DDIO and last level cache result to trips in memory that involve using up the available bandwidth. Prior work always assumed that memory latency was fixed because past NFV deployments would not generate enough memory traffic, as we indicate in the graph. However, as line rates go up and DDIO and last level cache contention become more pronounced, memory bandwidth utilization increases, and as a result, the increasing memory latency needs to be taken into consideration. In summary, contention in memory is a lot more nuanced than what prior work had assumed. Indeed, we showed that contention can manifest simultaneously and independently at least 3 different choke points in memory, with cache access rate only partly characterizing one of them. Modeling performance slowdown will require taking all these contention points into consideration. Let us now move on to our discussion about contentiousness and sensitivity. SLOMO draws inspiration from 2 key concepts introduced by prior work in the microarchitecture community. These concepts are called contentiousness and sensitivity. Contentiousness quantifies the amount of pressure a set of competing NFs applies on the shared hardware resources. Sensitivity, on the other hand, quantifies how susceptible the target NF is to competitors' contentiousness. SLOMO leverages these 2 concepts to predict the target's performance drop. Contentiousness is a property of the competing NFs and conceptually captures the pressure in terms of shared resource utilization that the competing NFs apply on the shared hardware resources. To understand this idea better, we see an example of the familiar by now target firewall in 2 collocation scenarios with competitors of different contentiousness. In the first case, the competitor is occupying a large part of the cache, which is accessing frequently, whereas in the second case, the competitor occupies a much smaller chunk of the cache, and in this time it doesn't access it as frequently. Intuitively, we can see that the first competitor is more contentious than the second one, as his larger occupancy and cache access rate can trigger more evictions to DRAM for the target NF. Sensitivity is a property of the target NF and quantifies the idea that the target NF is susceptible to performance drop due to competitors' contentiousness. Indeed, in this visual example, we show originally the case where the firewall runs alone on the server and occupies a share of the last level cache and achieves a certain level of throughput. Once a competing NF is added to the mix, the competitor starts occupying its own share of hardware resources and might thus cause slowdown for the target NF. We define the target sensitivity as the function that estimates the target slowdown relative to the competitor's contentiousness. Now, having introduced these key concepts, let's discuss SLOMO's challenges and how the design addresses them. SLOMO consists of an offline and an online component. Given a library of available NFs, SLOMO's offline component is responsible for profiling each NF for contentiousness and sensitivity. In real time, SLOMO takes as input a target NF and a set of competitors. The first step of the online process is to compose the aggregate contentiousness of the competitors and then provide that value as input to the target sensitivity function in order to predict its throughput. Naturally, realizing this design entails several open challenges. With respect to the offline component of SLOMO, a first challenge is that of identifying the metrics that sufficiently quantify the contentiousness of the competition. Having done that, the second challenge is that of modeling an NF sensitivity to contention. With respect to the online component, a key challenge is that of composing the aggregate contentiousness of any set of competing NFs before SLOMO provides it as input to the target sensitivity model. In this presentation, we will focus only on the first two questions. Let us begin with the first challenge. We first look at how SLOMO quantifies the contentiousness of any mix of competitors. The existence of many independent sources of contention intuitively suggests that SLOMO should rely on more than one metrics in order to measure their contentiousness, rather than a single metric like cache access rate. We identify an opportunity in using the PCM hardware counters, which can expose the competitor's resource utilization at multiple granularities through hundreds of candidate metrics. However, what would be a practical set of contentiousness metrics in the context of SLOMO? Overall, SLOMO uses less than 15 different PCM metrics to characterize contentiousness at all choke points. To show that SLOMO needs multiple metrics, we run two different experiments and measure the correlation between each PCM counter and the target's performance. In the first one, competitors only stress the DDIO subcache, whereas in the second one, competitors stress the last level cache. In the case of contention in the DDIO subcache, we observe that the most important metrics of contention are those associated with main memory bandwidth. On the other hand, in the case of last level cache contention, LLC metrics, perhaps unsurprisingly, exhibit the highest correlation of performance. Hence, we can only conclude that contentiousness is indeed a multivariate quantity and should be modeled as such. Let us now move to the second challenge, which is that of modeling the target sensitivity. Recall that sensitivity is the function that takes the competitor's contentiousness as input and returns the performance of the target in the presence of this competition. Intuitively, modeling sensitivity is a simple regression problem. However, our attempts to model it with simple techniques, such as linear regression, proved inaccurate. To understand this observation, we looked at how the sensitivity function looks like in practice and observed that it is a complex function of contentiousness. Let us look at some examples. In this example, we're looking at NF sensitivity as a function of competing cache access rate and L2 accesses. Here, we're looking at the sensitivity of the same NF, but this time as a function of cache occupancy and memory bandwidth. Finally, this is the sensitivity of a second NF, seen as a function of competing occupancy and cache access rate. How can SLOMO model this complex behavior? Our key insight with regards to modeling is that sensitivity exhibits clear phase transitions, or in other words, sharp changes in the performance of the NF as a function of increasing contentiousness. For instance, in this graph we show the sensitivity of a VPN as a function of competing cache access rate and LLC occupancy. What we can easily observe is that as LLC occupancy crosses a critical threshold of roughly 14 megabytes, the VPN's response to contention changes drastically. Before that, the NF experiences minimal performance drop as a result of contention, whereas after it, the drop becomes more pronounced. So this raises a question: what is the right modeling technique to model this function? SLOMO's approach is that of viewing sensitivity as a piecewise function of its inputs. Using that logic, we can model each area individually using a simpler, localized model and then combine the weaker models into one robust end-to-end sensitivity model. Fortunately, the machine learning literature provides us with a broad class of techniques to achieve that goal, called ensemble methods. We choose a well-known technique called gradient boosting regression. Finally, for the final challenge, regarding contentiousness composition, I urge you to read the detailed analysis in the paper. Before we conclude this talk, let us take a look at some key evaluation results. In our evaluation, our setup consisted of two directly connected servers, one hosting the NFs and one generating traffic. We experimented with two distinct server configurations, as shown on the slide, and followed all standard NFV deployment assumptions as discussed in our paper and in prior work. We experimented with a broad class of network functions, which consisted of research projects such as Click and NetBricks, and more industry-grade NFs such as Snort or Suricata. In our experiments, target and competing NFs were picked from that list. To evaluate SLOMO's accuracy, we compared its predictions with two prior works. The first is a predictor by Dobrescu et al., which focused on building a cache access rate-based model, and then Bubble Up, a prior work by Mars et al. That predicts performance drop as a function of the working set size of the competition. In this graph, we plot the prediction error of SLOMO alongside the two prior works for a variety of experiments for each NF. We observe that SLOMO achieves an average error of less than 8% and outperforms prior work by up to 60%. It is interesting to point out that for NFs where the prediction error of all frameworks is close to zero, that is because these NFs make very little use of shared hardware resources, and as a result, they're not particularly vulnerable to contention. Finally, we look at how SLOMO's predictions can inform efficient NF placement decisions such that the cluster server resources are used optimally. Using as a baseline the scenario where all NFs were optimally deployed across servers, SLOMO incurs less than 2% overhead in terms of number of servers needed. Rescue, a prior work from NSDI team that argued in favor of preventing contention altogether among competitors using a cache partitioning tool, incurs 6% overhead and few SLA violations. Finally, Dobrescu's conservative cache access rate-based approach results in 14% server overhead. As we can see, SLOMO improves cluster utilization without incurring SLA violations. These final remarks conclude my talk. Contention-aware performance prediction is critical for NFV orchestration, and while prior works have offered invaluable insights into the mechanisms of contention, existing predictors cannot capture all facets of memory contention and thus prove to be inaccurate. In our work, we observe that contention happens independently at multiple choke points in memory subsystem and leverage this finding to design SLOMO, a contention-aware performance predictor. SLOMO draws inspiration from a microarchitectural blueprint for modeling slowdown through contentiousness and sensitivity, and uses practical ML models to capture these properties of core-running NFs. SLOMO is accurate than prior work, and ensures up to 15% better cluster resource utilization. You can find the code online, and I'm looking forward to answering your questions. Thank you very much for your attention.